Okay, in this video we're going to talk about section 10.2. This is on correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. When you see a pattern in the data, you say that there is a correlation in the data. Although in this class we're only going to deal with linear patterns, patterns can also be exponential, they can be logarithmic, they can be periodic. And to see these patterns, you would draw a scatter plot of the data. We looked at going over a scatter plot in our last class, how we could create a scatter plot in a TI-83 at least. Remember that we should be reading graphs from left to right, the same as we read words. If the graph goes up, the correlation is positive, and if the graph goes down, the correlation is negative. The words weak, moderate, and strong are used to describe the strength of the relationship between the two variables. Let's look at a few examples of some correlation graphs. In this first example, we have some moderate positive correlation between these variables. In this second graph, we have a strong positive correlation, or a strong positive relationship between these two variables. In this third example, we have a perfect positive correlation. Notice that you could actually draw a straight line that passes through all of these points. If I can get the tool to cooperate, you can draw a straight line that passes perfectly through all these points. So in this case, there's a perfect positive correlation. In this fourth example, we have a negative correlation. We would maybe say this is like a moderate negative correlation, the same way that the one right above it is a moderate positive correlation. In this fifth example, there is no correlation. Notice that the scatter plot doesn't seem to form a pattern at all. And in the last example, we have a nonlinear correlation. Notice that in this case, the scatter plot seems to form like a U shape, like a parabola, right? You can draw a curve through these points. So there's a correlation here, but not a linear one. We also need to find, we need to find something called the linear correlation coefficient to describe the strength of this linear relationship between these two variables. This is also called the Pearson correlation coefficient, after Carl Pearson, who developed this. The symbol for the sample linear correlation coefficient is a lowercase r. The symbol for the population correlation coefficient is rho. This is not a p. This is a Greek letter. This is rho. There's a slight difference, right? This is a little bit more rounded. The formula for R for the correlation coefficient is SSXY divided by the square root of SSX times SSY. And recall from 10.1 that SSX is this sum, the sum of the difference of the squares between the x values and x bar. SSY, the sum of the difference of the squares of the differences between y and y bar. And then we have SSXY. Remember, these things are kind of cumbersome to compute by hand. So typically for this kind of stuff, we're going to end up using a calculator to assist us. There are some assumptions for the linear correlation. These are the same as the assumptions for the linear regression line. The set xy of ordered pairs is a random sample from the population of all such possible xy pairs. And we need to determine if we have a normal distribution, if our random variables have normal distributions. We can see if the scatter plot has a linear pattern, or I suppose maybe this is like an and or. Examine the residuals to see if there is randomness. So we can find the residuals, plot the residuals, and determine, is there a pattern in the residuals? If there is a pattern in the residuals, then there's going to be an issue in the data. You want your residuals to appear random. So let's look at how to interpret this correlation coefficient. The correlation coefficient is always going to be between -1 and +1. R equals -1 means that there is a perfect negative linear correlation, and R equals 1 means there is a perfect positive correlation. The closer R is to 1 or -1, the stronger the correlation. Careful. R being equal to 0 does not mean that there is no correlation at all. It just means that there is no linear correlation. There might be, for instance, a very strong curved pattern, meaning that you get this R value that is close to 0, because in that case there would not be a linear correlation. Let's look at picking up from an example that we looked at last night. How strong is the positive relationship between the alcohol content and the number of calories in a 12-ounce beer? To determine if there's a positive correlation, a random sample was taken of the beer's alcohol content and calories for several different beers, and the data are presented in the table below. We want to find the correlation coefficient and interpret that value. So, to find the correlation coefficient, what we have to do is use our calculator. That was from a previous, that was not from this example. I have data in here from a different problem, so I'm going to clear my lists. So we're going to go to stat edit. We want to enter the alcohol content in L1 and the calories in L2. I guess I don't know. Let's see, 5, 4.7, and 6.2. Let me see if I can make this a little bit larger on here. There we go. That should be a little bit easier to see. And now that we have all of our data entered, we can go to stat, tests, and we want to go to linreg t-test. Want to make sure our X list is L1 and our Y list is L2. We talked about how to choose this last class. In this case, our choice here shouldn't make a difference. We were asked, is there a positive correlation? So since we were asked if there's a positive correlation, we can choose this greater than 0. It shouldn't make a difference for what we're being asked for this problem. And we need to scroll down until we see R. We see here the correlation coefficient R. R is 0.913. So we get that R is 0.913. This is close to 1, right? So since this is close to 1, we would say that this has a strong positive correlation. Oh, sorry, I just realized I was covering that up with my calculator. Because this correlation coefficient, 0.913, is close to positive 1, we would say that we have a strong positive correlation. The next thing we need to discuss is this idea of causation. One common mistake that people make is to assume that because there is a correlation, that one variable causes the other. This is usually not the case. This would be like saying that the amount of alcohol in the beer causes it to have a certain number of calories. However, fermentation of sugars is what causes the alcohol content. The more sugars you have, the more alcohol can be made, and the more sugar, the higher the calories. It's actually the amount of sugar that causes both the alcohol content and the calorie count. Do not confuse the idea of correlation with the concept of causation. Just because two variables are correlated does not mean that one causes the other to happen. This is very important. Two variables being correlated does not mean that one causes the other to happen. Let's look at some examples. A study showed a strong linear correlation between per capita beer consumption and teachers' salaries. Does giving a teacher a raise cause people to buy more beer? Does buying more beer cause teachers to get a raise? Well, no, right? Neither of these things cause the other to happen. This is just a matter of when people have more income, they're going to be more likely to spend them on luxury goods or things that they may not have purchased otherwise, right? Or a study shows that there is a correlation between people who've had a root canal and those that have cancer. Does that mean that having a root canal causes cancer? No. Just because there's a positive correlation doesn't mean that one of these things causes the other, right? For instance, it turns out that there's a positive correlation between eating carrots and having cancer, but that doesn't necessarily mean that eating carrots causes cancer. There are lots of relationships that you can find between two variables, but that doesn't mean that one causes the other here, right? Maybe there's some maybe there's something that makes you both predisposed to have dental issues and have cancer, right? So just remember that correlation only means that a pattern exists. It does not mean that one variable causes the other variable to change. We also have this idea of explained variation. As we stated before, there's some variability in the dependent variable values, such as calories. Some of the variation in calories is due to the alcohol content, and some of the variation in calories is due to other factors. How much of the variation in calories is due to the alcohol content? So how much of this variation has our model explained? When considering this question, you want to look at how much of the variation in the calories is explained by alcohol content and how much is explained by other variables. Realize that some of the changes in calories have to do with other ingredients. You can have 2 beers at the same alcohol content, but one might have higher calories because of the other ingredients. Some variability is explained by the model, and some variability is not explained by the model. Together, these give the total variability. So this is total variation is explained variation plus unexplained variation, or sum of y minus y bar squared is equal to sum of y hat minus y bar squared plus sum of y minus y hat squared. So the proportion of the variation that is explained by the model is r squared. This is the explained variation divided by the total variation. This is also known as the coefficient of determination. To find this coefficient of determination, we square the correlation coefficient. So in addition, r squared is actually just part of your calculator results. So if we look at our calculator and we look at the results that we got from this, notice that it actually tells us the r squared during this Linreg t-test. This is pretty convenient. So if we were asked, find the coefficient of variation in calories that is explained by the linear relationship between alcohol content and calories, and then interpret this value. What this is asking for is the r squared from the previous problem that we did. So the r squared here is just 0.834. And what this means is that 83.4% of the variation in calories is explained by the linear relationship between alcohol content and calories. That's how we can interpret this coefficient of determination. The remaining percentage, the 16.6% remaining variation is going to be due to other factors. So a really good coefficient of determination has a very small unexplained part. I'd say this is pretty good. And let's look at this next part. This is a MyOpen math problem from the 10.2 homework. This is asking us at the 0.05 significance level, does the data below show significant correlation? To figure this out, we first have to enter this data into our calculators. So I'm going to clear my two lists, clear list, L1, L2. Let me make my calculator a little bit larger to make it easier to see. So now stat edit. This first list L1 is just the numbers 1 through 12. And for L2, we type in L2. Almost made a mistake there. And we're going to go to stat, tests, linreg t-test. L1 is xlist, L2 is ylist. Here we're asked, does the data show significant correlation? So we're not asked, does it show positive correlation? Does it show negative correlation? We're asked, does it show correlation? So we're going to choose this not equal to 0. And we're going to hit calculate. Notice that this gave us a significance level, right? Here, notice that the linreg t-test gives us a p-value. This p-value is really small, right? 4.248 times 10 to the negative 5 is our p-value. So in this case, this p-value that we're given is way smaller than this alpha value that we were given, right? So because our p-value is less than our alpha value, right? This 4.248 times 10 to the negative 5 is way less than 0.05. We would say that there is significant correlation. And I believe with that, you have all that you need.